So that was the delayed oscillator with negative feedback related to the wave reflections both from the eastern boundary and the western boundary. This one is called the recharge-discharge oscillator from Fei Jin. The idea of recharge was there before. Klaus Wertke had already talked about in the 1970s based on observations of the warm waters in the West Pacific. He argued that before El Nino, warm water is loaded up and it's like a gun, and then somebody pulls the trigger and then El Nino happens. So the idea of recharge and discharge was there. Fei Jin put a nice mathematical structure to it with some idealizations. So he looks at the anomalies of the depth of, let's say, the thermocline in the east as a function of the depth of the thermocline in the west plus a wind. So if you remember, the wind is pushing water to the west and creating a slope to the west in the sea level and a slope to the east in the thermocline. So he related the wind anomaly forcing to the thermocline slope adjustment on El Nino timescales. And remember that what is additional here is coming from our Sverdrup theory, where we had said that if there is a wind stress curl, then we can derive a meridional mass transport, integrated meridional mass transport that is related to the curl of the wind stress. And since this is beta, there is no problem computing this on the equator. This is not F. So you can actually take the wind anomalies that we just alluded to and look at their meridional decays, and obviously ends up with wind stress curls, and that will create a Sverdrup transport. So you're not just advecting and creating waves, you're actually creating Sverdrup transport by this mechanism. And you can think of it as transport above the thermocline, which explains why the slope flattens and also the thermocline shoals or shallows in the mean depth, because you have discharged the warm water poleward. And then when La Nina happens, you are going to change the wind stress curl and start accumulating by Sverdrup transport mass into the deep tropical box in terms of warm water recharge. Okay. Then he said the West Pacific thermocline anomalies times variability is related to a process of damping that is got this Sverdrup transport. It's got the dissipation term because of the wind. There is a negative let's see. Okay, so this wind is giving you variability of the anomaly in the west, and that is actually related to the mean, that is, or the anomaly response that is balancing the east-west gradient. So that wind anomaly is related to this tau bar with some coefficient alpha. These are kind of simplifying assumptions, but you can read the paper to look at the justifications. But you can see how simple the equations are. Okay. As we saw before, the annual cycle and the El Nino evolution and its phase locking are basically similar. These are called self-similar systems, and they have certain properties that we won't get into, but El Nino and the annual cycle are basically self-similar in that sense. That explains why there are these close relations between wind stress, sea level slope, thermocline, and how the anomalies are related to each other, and so on. Then you need an equation for time variability of the East Pacific temperature anomaly, which is related to this damping term in terms of minus CTE, plus it is related to the movement of the thermocline. Remember when I said when Bjerknes feedback happens, it's not just the surface fluxes. Movement of the thermocline is going to affect the sea surface temperature through these entrainment processes that are associated with the upwelling and the turbulent kinetic energy associated with the winds. So the winds do the Ekman divergence, but they also provide the turbulent kinetic energy to create mixing in the ocean, which is proportional to the wind speed cubed. Okay, that's something important to remember. Plus, there is a time scale, or the damping term that is associated with the wind stress, which you can think of as advection term or the wave term and so on, where the wind stress itself in the east is going to affect the heat budget. So this is a more complicated heat budget equation than the delayed oscillator, which didn't do anything with thermocline depths and temperatures explicitly. It just said the waves are going to adjust the thermocline to the east and to the west during the growing phase and the decay phase. Okay, so you can relate the East Pacific wind stress anomaly to the temperature and also the integrated equatorial wind anomaly that's giving you the anomalous balance between the sea surface height and the thermocline with these coefficients. And there are arguments we can use based on the physics that tell you that the B has to be greater than B prime, and that allows you to do some simplification. There is this negative relation also here, basically because if you have westerly wind anomaly, you are going to get a deeper thermocline. So yes, so positive wind stress anomaly is going to give you deeper thermocline. So that sign is taken care of by taking these terms in a proper direction. Okay, so essentially we are reducing the equations to a simpler set. So now you write the equation for the eastern part in terms of the western. So use the relation between HE and HW to replace HW in this equation and write it in terms of HE and TE. Okay, so why are we doing that? Basically because in the east is where the sea surface temperature variability is very high. That's where the ocean dynamic processes are very important. So it's better to move the action to the east, and that's where the upwelling, bringing up of cold water and the recharge processes are going to happen. So that's how you can think about it. So you can write that as minus RHW minus alpha BTE. So you are replacing tau alpha tau E with basically this term, and writing dt as R times TE plus gamma HW, where this is again the, you can think of it as the Birknes feedback term. Basically the movement of the thermocline is going to change the temperature, is going to change the winds, change the thermocline slope and the sea level slope. Okay, so R here is combination of those previous equations as gamma B, the coefficient, plus delta S times B prime TE minus C, where we can write this as basically B prime, since it's much smaller than B, we can write that as gamma B minus C. Okay, it's a simple set of equations. I don't know how much more to say about it. These are simple idealizations that take care of what are considered the most basic processes, the most important processes for the adjustment of the dynamics and the thermodynamics. So we are including the dynamics in terms of the movement of the thermocline and the thermodynamics in terms of the temperature equation. Okay, so that's in some sense much more complete than the delayed oscillator mechanism. So here, a small positive TE will lead to a basin averaged positive wind stress anomaly as expressed in the equations, leading to deeper thermocline in the east and shallower thermocline in the west, and a positive growth anomaly of TE. So we are getting all three quantities here. To a large degree, this growth of the warm phase is identical to the positive feedback in the Birknes mechanism. Evolution of the warm anomaly and the thermocline distribution appears schematically in the figure that we will look at in a minute. However, the wind distribution at low latitude drives a meridional spread of transport out of the equatorial region, which we will see in the figure as well. So it's not just the waves. Here we are actually including ocean dynamics in terms of the rate of transport. Thus the wind fields create a net export of mean zonal heat content to higher latitudes. So this is the heat discharge process. So during a La Nina and normal times, you have accumulated the heat, which is not only discharging to the east, but it's also being moved out of the deep tropics towards the poles in what is called the heat discharge. The discharge of heat out of the equatorial zone leads to a reduction of eastern Pacific temperature anomaly, producing a weaker zonal wind stress. So now we are using the east-west SST gradient and the slopes. Consistently, the tilt of the anomaly depth thermocline reduces towards zero. As a result, the discharge net thermocline depth across the entire near equatorial basin decreases. So the slope flattens, thermocline shoals. The consequence of discharge of heat from the tropics is a negative temperature anomaly in the east, and this is the negative feedback we are looking for and gives us the transition from warm to cold phase. Okay, so those equations also tell us that the West Pacific anomaly will increase while TE decreases. Includes the various thermodynamic terms that we looked at and the deepening of the thermocline, leading to a mature cold phase. So you have completely transitioned from a warm phase to a cold phase with this recharge-discharge process. At this stage, the resulting sphere of transport will lead to a net heat transport into the equatorial regions. This heat recharge phase of the cycle is shown in this figure. So let's just talk about the discharge recharge in the next podcast, and then explain the recharge discharge oscillator. Okay, because we have been saying these words recharge and discharge, and I've been saying that upwelling, heat absorption and advection west, growth of the warm pool and warm water anomaly and so on, but it's worth spending some time to understand that before we look at the figures of the recharge discharge oscillator. But the recharge discharge oscillator with the parameter space gives us very rich solutions, and then there is follow-up work talking about the meridional scale of the recharge discharge and how that can also give you the so-called ENSO variability, or the clustering of strong El Niños and weak El Niños from one decade to another, or from one set of decades to another set of decades, and so on. Okay, so this is a good theory. Again, this is more of a explanation of what is happening. Can you use it for making forecasts? Not quite. So that's the challenge that we have to face eventually.